Here is an example. Example 9.1. A 450 millimeter square interior column means we have to design the foundation for the interior column whose square column size is 450 millimeter by 450 millimeter. The column reinforcement is a reinforcement with 8 number 25 bars, means 8 number 25 bars are of the column. The grade of the steel for the column, that is FY420. Supports a dead load 700 kilonewton and live load 400 kilonewton. Assume that a live load reduction 30% may be allowed at the foundation level. Okay, means 30% live load reduction is allowed. The foundation is to be placed at a depth 1 meter where the gross allowable bearing capacity is 110 kPa, means 110 kilopascal. We have to place our foundation from the ground level at a 1 meter below. The average density of backfill material and the footing concrete together may be taken as 2100 kg per meter cube. While the filling from ground to the plinth level, means there is some fill on the ground, that is 0.5 meter of material with average density of 1800 kg per meter cube. Design a square footing using FC prime 20 megapascal, FY for foundation 300 megapascal, FY for double bars that will continue to the column, that will be 420 megapascal. Now in the solution the data is given. The QA allowable bearing capacity, that is 110 kPa at a depth 1 meter. Dead load 700, live load 400. Live load reduction is allowed, that is 30%. FC prime 20, FY 300 megapascal for footing and FY for doubles, that is 420 megapascal. Depth of footing where the foundation will be placed from the ground level, that is 1 meter below. Average density of fill and foundations means under the ground the average density will be used to 100 kg per meter cube. Density of surcharge means the above the ground level where we have provided the fill of 0.5 meter. Okay, their density is 1800 kg per meter cube. Now the total unfactored load, that is dead and live, and there is a 30% reduction, 1 minus 0.3, or you can directly write 0.7 into 400. So total unfactored load, that is 980 kilonewton. So we calculate the required footing size based on unfactored load that I have discussed in the slides. Now to calculate the Q net, that is the net bearing capacity at the level where the footing will be placed. So our footing is placed at 1 meter below. So we will subtract the overburden load that is present. Now Q net, net contact pressure will be calculated as Q allowable minus overburden, means the load which is present at the foundation level. So at the foundation level two loads are present. One is backfill and one is surcharge load. That is the load present up to plinth level. That is from foundation to ground level, and from ground level to plinth level, that both loads are present. You have to subtract both these. So 110 minus 1 into 0.5. 0.5 I will explain. Here 1 into density means gamma H. Gamma is 2100, H is 1. So that is the load. So here the 0.5 meter surcharge load 0.5 into 1800. So the backfill load, that is statement is given in the previous pages, that whenever you consider the backfill load, then you have to use the factor of safety 0.5. So you have to not consider the full, because that is a backfill load, and second the weight of the footing that will be again included in the design of the footing. So you no need to calculate the full load. So you have to consider the half for the backfill load. So here in the backfill load, that is a surcharge load on the ground level. So backfill is 1 into 2100 into 0.5 plus the surcharge load 0.5 into 1800, then multiply with 9.81 divided by 1000 to convert into kilonewton per meter square. So our Q net pressure is 90.87 kPa. So our required area of footing formula, that is applied load divided by pressure. Applied load, that is unfactored load, that is 980 divided by 90.87. So the area is coming 10.79. So take the under root of this value, under root 10.79 equal, that is 3.28. So just round it upward, that take 3.3 here, 3.3 by 3.3 meter foundation. So now we will calculate the factor load, that is 1.2 dead plus 1.6 live, and the live there is a 30% reduction. So 1.2 dead plus 1.6 live, 0.7, 70% load will be considered, 30% will be subtracted. So our total factor load, that is a 1288 kilonewton. Okay, so now, so what will be the pressure due to the applied load, factor load, and the area which you have calculated here, 3.3 by 3.3. So applied factor load divided by footing and area 3.3. So applied pressure, so that is 118.3 kPa. So now we will calculate the approximate depth of footing. That formula is given by this author, Concrete Structures by Zahid Ahmed Siddiqui. Approximate depth of footing H equal under root P plus 1.5 mx plus 1.5 my. And here 0.01 into alpha s into Fc prime. So P is the applied axial load, 1.5 moment in x, moment in y, 0.01 alpha is for center footing, that is 40, for edge footing, for corner footing alpha s value is given. So plus 60, that is calculate the approximate depth, so that should be equal or greater to 50 millimeter, that I have explained in the slides. So the ACA code, the effective depth, you can say a little bit, so that should not be less than 150 millimeter. So by adding the cover reinforcement, so author has generalized to 250 millimeter. So H, so our total here P is the load, that is the unfactored load. So multiply with 1000 divided by 0.01 into 40 for interior footing, multiply with 20 Fc prime plus 60. So our approximate depth is for 10 millimeter, say rounded up to nearest to 75 millimeter. So for 10, say 450 millimeter. So for effective depth, that is the footing depth that we have decided, that is 450 millimeter minus 60. So our effective depth is 390 millimeter. So B naught, that is the effective perimeter in the punching shear. So here, so in the punching shear C1, C2, that is the column dimension, and in the C1 in this direction D by 2, similarly in this direction D by 2. So you can say C1 plus D, full D, C2 plus D, so you will get two lengths. C1 plus D, C2 plus D, you will get two lengths, then multiply with 2, you get the total perimeter, this length, this length, this length, this length. For all four lengths, you will get the perimeter B naught, 2 times C1 plus D, C2 plus D. So you are getting the perimeter value, that is 3360 millimeter. Beta is the column dimensions ratios, shorter dimension to longer dimension to shorter. So longer and shorter are same, 450 by 450. So beta is 1. So our 5 EC value lesser of the following three, 1, 2 and 3. So first formula 0.75, 0.33, lambda 1, under root Fc prime 20, B naught 3360, multiply by effective depth 390 divided by 1000 to convert into kilonewton. Our first answer is 1450. Second is 0.75 into 0.17 plus into 1 plus 2 by beta. Our beta is 1 and lambda 1 under root FC prime 20, B naught value 3360, D 390. Okay, here in the second formula divided by 1000, 2241. The third formula 0.75 multiplied by 0.083 alpha S, that is 40 for interior footing, D 390, B naught 3360 plus 2, 1 under root FC prime, B naught, D divided by 1000. So we are getting the shear capacity, 3 shear capacity values. So lesser of these 3's, that is 1450. So that will be our shear capacity. Now applied shear, that will be QU into total area, that is 3.3 square footing area minus effective area, which will comes in the punching. Okay, so that is C1 plus D into C2 plus D. So you will subtract the area for punching and you are getting the applied shear value for two-way shear, that is 1204.8. So our capacity is 1450. So our capacity is more than applied shear, so our check is okay.